Welcome, AP Stats students, to yet another exciting edition of Special Problems. This particular special problem is for our Chapter 2, and as we've mentioned before, these are basically practice AP test questions. All right, so this one is about chips. Have you ever really thought that much about chips? Okay. This problem says a manufacturer of corn chips is labeling their bags with a net weight of 10 ounces. I've done this problem before and I've always wondered, hey, what happened if I actually did weigh some bags of chips? So guess what I'm gonna do right here? I got my scale right here. There we go, turn that thing on. And let's see, it's zeroed out. And I got some bags of chips. So here's a bag of chips. It's labeled 1 ounce. Let's see what it says when I put it on my scale. 1 1/8. Let's try another bag. So I got another bag here. Also again, labeled net weight, 1 ounce. See what my scale says. Look at that, I'm a lucky guy. I've got 2 bags of chips and I've got an extra 1/4 ounce for my money. Really cool. Let's try another bag. Again, it's labeled somewhere. There it is. Other side on this bag. 1 ounce. Let's try that one. Oh, look at that. That one's right on 1 ounce. But again, my scale is actually only accurate to 1/8 of an ounce. So it could be slightly under or slightly over, and it's just rounding to 1 ounce. All right, let's try another bag. And again, this one says 1 ounce. Give it a shot. That one's 1 ounce again. So I have more bags of chips, but I think you get the point here. Is every bag of chips going to weigh exactly the same? Right? That's kind of the point of our class, right? At this point, hopefully you're starting to realize that, you know what? That's not how the world works. There's some random chance involved, right? Not everything is exactly going to be 1 ounce, or in this case, not every bag of chips is going to be exactly 10 ounces. Some might be a bit over, some might be a bit under. That's called randomness. Okay, and realize my bags that were slightly over, right? I could open the bag up. I'm not going to, but I could open my bag up. I could take out a chip and reweigh it, but guess what? Now it might be slightly underweight, right? That's the whole point. Each chip will be slightly different in weight. Some will be a little broken, others won't. And there's really no way to ensure that every single bag weighs exactly 1 ounce, or in this case, exactly 10 ounces for the size bag they're talking about in the problem. But here's the thing. The machine that's filling the bags will follow a normal distribution. It will have some mean and it will have some standard deviation. That's where stats is going to come in. So question A. Suppose the manufacturers decide to set their machine to 10.3 ounces per bag. Makes sense, right? You just saw me weigh 4 bags. 2 of them were overweight and 2 of them weren't. So maybe they're purposefully slightly overfilling the bag to avoid customer complaints or even lawsuits, right? Anyway, they know that their machinery has a standard deviation of roughly 0.2 ounces. So their question is, what percentage of the bags that they fill with their chips will actually weigh less than the advertised 10 ounces? Because again, they don't want to be sued, right? Okay, so here's how it works. We know this is just a standard normal calculation, right? So we have a normal distribution, a given mean, and standard deviation. So the question is, when will my random variable, in this case my random bag of chips, weigh less than 10 ounces? And you can see I started the calculation, and then I went to grab from my calculator and realized, uh-oh, I forgot my calculator. So this is take 2. All right, so put in my standard deviation here. Okay, work this out, and that is a z-score of negative 1.5. So the way they've set up their machinery, for their bag to be underweight, it would have to land 1.5 standard deviations below the mean. Okay. Now at this point you could either use your table A or, you guessed it, the handy dandy calculator that I had to go get. Okay, so again, it's in the distribution menu because I'm talking about a normal distribution. So I go there, and this is a normal CDF, cumulative density function. It's a left tail, so my lower bound is negative infinity. Remember, we don't have an infinity key. This is scientific notation. So -1 times 10, or actually, it's 1 times 10 to the negative 99th power, but yeah. Okay, my upper bound is 10 ounces. My mean is 10.3, and my standard deviation is 0.2. Now, I could have done this in terms of z-scores, right? I could have said negative infinity, negative 1.5, 0, and 1. You get the same answer. That's how your table A works, right? And there you go, 0.0668, blah, 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 blah. So answering their question, they want to know what percentage will weigh less than advertised. So about 6.68% of bags will be underweight. Okay, but a lot of bags will be overweight. So again, maybe take that scale with you to the grocery store when you go shopping for chips. And please realize this would apply to more than just chips, right? Anything that's being labeled with some weight and filled is going to have some that are underfilled, some that are overfilled, and some that are kind of right on. Okay, so here's B. This is kind of the whole point. They're worried, right? They don't want customers upset that they're getting gypped out of chips. So they decide they don't want more than 1% of the bags being underweight. And you can see that their current system is making more than that underweight. So they have two choices. They can change the mean setting on their machines. Say, hey, let's put even more chips in each bag on average to reduce the number of underweight bags. Or they could adjust their standard deviation. In other words, make their machinery more accurate. Okay, so we have two choices. Let's calculate the new mean if we choose that, or the new standard deviation if we choose that, and then let's talk about which of those choices is more feasible. All right, so here we go. So we only want 1% underweight. Right? So we have a normal distribution. We want the left tail to be 0.01. We want to know, hey, what's this value right here, right? So we want the z-score. We want to know how many standard deviations we would have to be below the mean to make that happen. Okay, so again, table A, you can look up 1% and figure out the z-score. So you're doing an inverse normal, right? You're looking in the body of the table and finding a z-score from it. Or, again, calculator, distribution, and it's called an inverse normal because we're working backwards. We want 1% to the left, and I'm not going to mess with the mean or standard deviation. I'm going to go for the z-score here, standard normal. And there we go. If we are approximately 2.3, MSE3, to 6 standard deviations below the average, will be in the first percentile, right? Okay, so we now know that. Well, guess what? We can now calculate, hey, if I want to change my mean, there's the z-score. And we have some unknown mean, and the standard deviation stays fixed at 0.2. Okay, so here's how I calculate it. I don't actually use that. I use all the decimals that I already have in my calculator, right? Multiply that by 0.2, and then subtract 10, and we get negative 10 point whatever equals negative mu, so mu is positive 10.4, blah, 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 approximately. 6.5 ounces. Okay, so that's option 1. Leave your standard deviation at 0.2 and increase the setting for the mean on the machine to that. Okay, option 2. What if I change sigma? Okay, again, same z-score, because again, we only want 1% of bags underweight. We're leaving the mean setting at 10.3, and we're gonna change our sigma, okay? Okay, again, I'm gonna use my calculator with all the decimal accuracy. So I have negative 2.3 times sigma equals negative 0.3, so negative 0.3 divided by this answer will give me the sigma I'm looking for. So about 0.13 ounces. Okay, so those are the two options. We could increase our mean to this and leave our sigma alone, or we could decrease our sigma to this and leave our mean alone. Now, here's why it's an AP test question, right? This is just inverse normal calculation, straightforward stuff. But which of these two options do you think is more feasible? That's what makes it AP. Well, could I change the mean setting on my machine? Sure, not a problem. Could I make my machine, like change the standard deviation setting and make my machine more accurate? If you think about that for a minute, if you had such a setting, why wouldn't you already have it set to the most accurate setting, right? Who wants to be wasting product and overfilling the bags? So the fact of the matter is, you can't just adjust the standard deviation setting on your machine, right? It's fixed. That's the best it's going to do. So the only way to change the standard deviation would be to create a whole new machine that's somehow more accurate. But as I mentioned earlier, at some point, you're either under or overfilled. You put one more chip in, you're over, one less chip in, you're under. You're going to have variation, right? So the only way I could think of to get more accuracy would be to have a human, right, go grab, hey, this bag is slightly overfilled. Take a chip, break it, put it back in there and kind of adjust every bag manually, which again would be a real silly thing to do, a real hassle, right? Or we could smash all the chips down into a really fine dust, and then we could just pour that dust into the bag, and we could probably get pretty darn accurate weights that way. But it wouldn't be chips anymore, and I don't think anyone would buy them. So that's why they're asking this question. You need to think a little bit, and you need to realize that one's feasible. That one, probably not feasible. Okay, so change the mean weight to 10.465 ounces is the feasible option. And there we go. Okay, last question. Manufacturers have also discovered if they put too many chips in the bag could burst. That makes sense. I've actually had that happen. I don't know about you, but yeah, I've seen that happen. In order to balance their concerns over customer satisfaction and breakage of bags, they want to adjust the filling machine so that 1% are underweight, so they're not getting sued for cheating customers, but they only want 2% of the bags to weigh, a little typo there, more than 10.5 ounces. So this is like dream world. They're saying, hey, if we could do this, this would be the best case scenario for our business. So let's help them out. Let's find the values of mu and sigma that would accomplish these goals. Okay, so I'll start with, again, a little drawing. So we want that 1% on the left, and that's going to be our cutoff for being underweight. And then we're okay with 2% above 10.5 ounces. Okay, and we need to figure this out. Well, we know the 1%, it's normal distribution, right? So we already know that z-score right there is going to be negative 2.326, blah, 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 blah. Okay, we don't know this z-score yet, so let's look it up. Again, table A or your calculator, this is the inverse normal. We have the area. We want to know the number of standard deviations. Okay, so normal CDF. We have two options, right? This value has 98% to the left, or 2% to the right. On our table is left-tailed, so you'd have to look up the 98%. So I'll use my calculator that way. So, oops, sorry, I did normal CDF by accident. Let's see, get the right command here. Inverse, oh, I put it in the wrong spot. Okay, quit, start over. Inverse normal. And again, I could do a right tail with the 84, but if you're using your table, you got to do a left. So I'm going to say 98% to the left and leave it as 0 for mu and 1 for sigma. That's going to give me my z-score, number of standard deviations. And there we go. So 2.0537, blah, 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 blah. That many standard deviations above the mean will put me in the 98th percentile, or in other words, 2% above me. Okay. Now, you hopefully are realizing we have our z-score, we have this 10, we need to make an equation, right? Z equals x minus mu over sigma. So plug in that z. X is 10, but we are looking for a mu and we're also looking for a sigma. So hopefully you're realizing, hey, this equation has two unknowns and it's only one equation. How the heck do I solve it? Well, that's why they gave you this other point on the distribution, right? Use that to create a second equation. So that's going to give me the equation of 2.0537 equals 10.5 minus mu over sigma. And now I have two equations with the same two unknowns. So solve either one and use substitution, or I guess you could use elimination, right? That works too, your choice. So solving this, let's see, negative 2.326 sigma equals 10 minus mu. This one is 2.0537 sigma, 10.5 minus mu, right? And then you could, I guess, line those up and do elimination. And now I've eliminated my mu, and I can get, what is this, negative 4 point, blah, 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 blah. Sigma equals negative 0.5. And divide this out, and we'll get our sigma, which is 0.11415727, blah, 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 blah. There we go, there's our sigma. Now we'll go ahead and plug that back into either of our original equations and solve for mu. And we'll find that mu is 10.2655, blah, 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 blah. Okay, so to answer the question, in their dream world, if they could create a machine that has a normal distribution with a mean of 10.27 ounces and a standard deviation of 0.11 ounces, they could meet their goal. Okay. Now, again, this is kind of fantasy land because notice that's even more accurate than letter B required. So we probably can't get a machine that's that accurate, not to mention even if our machine were as accurate as possible, we don't really know with the weighted chips and the filling if it's even possible. So, but we can tell them, hey, this is your goal. If you could get there, that would be great. And they can investigate and see if it can happen. Okay, so there you go. Hopefully you learned a lot about stats and maybe a little bit about filling bags of chips watching this video. And thanks for watching.